So here we have a three-dimensional geometric description of vectors. So I've chosen three vectors randomly. So U, the first blue one, is 1, 4, 3. V is -9, 2, 0, and W is 2, 1, -1. That's cyan one shooting off down this way. So three-dimensional vectors function the same way as two-dimensional ones. We describe them using the location where the tip of the arrow ends, and the origin is always the tail. Alright, and then to add them together, we in fact do the same thing. So here's the image if we wanted to add W to U. So we have the blue arrow coming out of the origin first that I'm pointing at now. Alright, and then the red arrow jumping off of the blue arrow, that's our translation of V. And then the black arrow, the big one down the middle, that is the sum of U and V. So geometrically, three-dimensional vectors work the same way as two-dimensional ones do. Algebraically as well. Right. Let's take a look real quick at scaling before we get too far. So if we want to take from the origin, which I've labeled O, to U, and then we want to color that as blue still. Let's stick the arrow from the origin to pi times U. Actually, I believe that's a capital Pi times U. Alright, and let's make that, let's go orange. Alright. Oh, look, it's a lowercase p. Alright. So we see here the blue arrow, you can barely see, but it's at the bottom. We can see the tip of it partway through, and then the orange one is the pi scaling of U. So that is three-dimensional vectors. I'll leave n-dimensional vectors for you to just think about. Oh, I have some pictures here from making the animation on the Canvas page. So anyway, I just wanted to show you that real quick. It's a lot easier to visualize using Sage here. I'll scroll up so you can see my code again. So we again said U, V, and W are vectors. O is the zero vector in three-dimensional space. And then our image is just consisting of a bunch of arrows where we tell them the tail, the tip, and the optional argument of the color. Alright, excellent. Have a good one.